Professor Mandal.
Okay, so I'm going to talk about the arrow of time, which is the following: that suppose you consider some of the day-to-day events, like take a cup of hot tea. It just gets cold. It never so happens that it just takes heat from the atmosphere and gets hotter and so on. You put some sugar in that tea and the sugar dissolves. It's not like the dissolved sugar ever comes out of it. So these things are day-to-day occurrences. These are events which show the so-called arrow of time. Now, we never bother about these, but there is some fundamental conflict of these events, an apparent conflict of these events with the fundamental laws of physics, like the laws of Galileo. That's the law of inertia, that something that moves will keep moving forever, and something that is stationary, that remains stationary forever. These situations, all exhibit perfect symmetry with respect to the past and the future. If you take two snapshots, you can never tell apart which one is past and which one is future. So, there seems to be a fundamental conflict here. So, how do we resolve these conflicts? In fact, there are not only these arrows of time in day-to-day life, but there are also arrows of time on a larger scale, like the arrow of evolution of species, the cosmological arrow that the universe expands, and so on and so forth, and the arrow of the black hole, which is that something can be absorbed by a black hole, but it never spits out that object, that violates some law of gravity. So, there seems to be this bundle of contradictions. So how do we resolve these conflicts? And can we also say the relation between these various arrows? So these are things which I'm going to talk about, and partial resolution of these conflicts. And please watch us.
Actually, you would have liked to relax a bit, but thanks coming here. Chandwai is a forum of TIFR to take excitement of science to people. We talk about current science, so we talk about various other topical subjects also, right from share market to everything else. So first Sunday we are in Prithvi complex, either at the Prithvi Theatre or at Prithvi House. Third Sunday we are at 2 Science, Rupal College, opposite Matunga Road Railway Station. The next talk is about plasmonics, taking light into the nano world, and this is being delivered by Achanta Venugopal of TIFR, DCMP and MS, that's the Department of Condensed Matter and Material Sciences. And well, nice to see you all there. Following that, we have a talk about gravitational lensing, and I will request today's speaker to talk about a small introduction. We did not have any details to add on other than except the picture. So he will give you a small glimpse of the gravitational lensing also. Following that, well, we had thought of doing a Diwali special, actually November being a Diwali month, but we thought of not repeating ourselves, and hence have tried to refrain. But still we have somebody who will talk about photosynthesis, again light, and he's also going to talk about trying to synthesize energy from the same solar source. Can we mimic the nature and try to make solar cells? So do come for that Chandwai on November 18th at Rupal College. And okay, fine. Most importantly, there are someday in future when Ramakrishnan is going to talk about microkelvin refrigerators, and GRK. Actually, he was there to talk in November, but all of a sudden he had to go to the US for an emergency meeting. Most of you people have joined us last year for night sky observations, where we conducted it in a place called Lavali near Badlapur. You really need to go away from the city light, otherwise the city light pollution kills all the night sky. So any of you enthusiasts of looking at what the night sky looks like and want to learn more about it are welcome to participate. We'll put out the notices to this effect on our Facebook page and also on our pages at the TIFR website. So I will request Noirith today to introduce the speaker and take charge of the proceedings. Yes.
So would any of the TIFR astronomers be there for the night sky observation?
Yes. We have a team of our own students who keep on talking about various different aspects of astronomy, and we conduct night sky observations in 3 shifts: early morning, early evening sky, or then the midnight sky, and then early morning sky. In between those gaps, we have dinner, tea, but we also have informative talks about why do astronomy, and we also talk about different length scales and energy forces working, or energy and other forces acting at different length scales, and various other things about astronomy, the future telescopes and blah blah blah. Dipankar here talks about it, Mangesh talks about it. We all have an entire team which talks about all these details of astronomy. This is normally held around the new moon day. So we hold our camps 2 or 3 days before the new moon, and we continue also 2 days after the new moon. You know, that time this night sky is darkest. So actually, very frankly speaking, me and Vinita Navalkar, our another observer, we feel that even the moon on a full moon day is fabulous to look at, and close to the 10th to 13th day, you can see a lot of craters and other things. You can do the moon mapping, and we will have another moon mapping session certainly at least once this year. Also this year, November, you will see the sun is at the peak of its sunspots. So we will have that also observations arranged sometime in the day, but that will be from TIFR, and I really do not want to open it to all the people, but college students would really be welcome there. So there are several other security and other essential problems that we have to face and we have to tackle. So we'll take appropriate action at that. We will notify you on our Facebook pages as well as on our TIFR pages. See, all our events are communicated to you by the emails, by Facebook, and via the TIFR web pages. So that's the standard operating procedure now for us. We'll do that. Yeah. If you have not enrolled yourself, please go to Facebook page, like it. You will automatically be added to the list. Otherwise, you can send an email to me at outreach@tifr.res.in. You will be added to the list. Don't worry. And you also have exit point. All our emails have a line at the bottom. Just type unsubscribe and send a reply. No need to write anything. No justifications asked. You will remove it from the mailing list. No obligations. Noiri, please take over.
Hi, welcome to another session of Chai and Wine. Today we have with us Professor Gautam Mandal. Professor Gautam Mandal did his BSc in Physics from Presidency College, Calcutta, and then he joined TIFR for his PhD. Then he did his postdoc in Princeton Institute of Advanced Studies and came back here as a professor in the Department of Theoretical Physics. He's a very, very well-known string theorist. Today he will talk about the arrow of time and many fascinating aspects of everyday life. Why do videos played backwards look weird? And many other interesting topics. So we'll take a ride with Professor Gautam Mandal.
Can everybody hear me? Back there? Okay, so I'm going to talk about the arrow of time, and I'm going to explain what it is. Right? And so please stop me, in the middle, because of course there is some mingling session after the talk, and you can ask me any kind of questions at the time. But sometimes people forget, what was being talked about. So you can stop me during the talk, as often as you please. That freedom has been given to me by Suren here, so that the talk itself can be extended a little beyond its stipulated half an hour. And so basically it's some fun stuff, and please enjoy. And it has some bearings on fundamental physics. I'm not going to say that all the puzzles that I'm going to present here are solved. Then there's no fun. Okay, they're unsolved questions, and the answers will come from young people in the audience, such as over there, and so on. So that's okay. Let's start. Good. So the topic is the arrow of time. So what is an arrow of time? So we say that an event exhibits an arrow of time if pictures of that event taken at various times if they're randomly, sort of shuffled about, then they can be correctly ordered. Okay? A very simple example is the growing up of human beings. So here it is. It's incorrectly ordered. Okay? Everybody agrees with me this is incorrectly ordered? Okay? So here it is. Now this is correctly ordered. Everybody agrees with me. Okay, so growing up, therefore, is an event which exhibits an arrow of time. Not everything does. Like if I show you the picture of a new moon and a full moon, which one is before? Which one is after? Okay? Keeps repeating. So there is no arrow of time in that one. So this growing up shows an arrow of time. And so this is in a small scale of human life. So here it is. It goes this way. Everybody agrees with me here. On a somewhat larger scale, a few million years, there's another arrow of time. So this is human evolution as found out by Mr. Darwin. So here everybody agrees with me, hopefully, that the arrow of time goes from left to right. Yeah? Okay, so this is right. Okay, and this is wrong. Hopefully, we are not going in that direction. So this exists on an even larger scale, a few billion years. That's the cosmological arrow of time. Okay? This is a little unfamiliar to some members in the audience perhaps. This is, so let me show you what this object. So here, time is supposed to run from left to right. Okay? So what's happening here is that this object, this here, okay, is the beginning of the universe. Okay, that's called the Big Bang. And it expands, like this. So here it was some very hot, very dense, soup of particles, and those particles all get colder, galaxies form, we get formed, etc., etc. Okay? So cartoon is like this, that it's like, the surface of the universe is like the universe itself is like the surface of an inflatable balloon. The balloon is being inflated, and if you are given snapshots like this, you can figure out which one was before and which one is after. So that's the cosmological arrow of time. Of course, these are, sort of cosmic things and so on and so forth. So let's go back to the arrow of time in everyday life. Okay? So let me say another definition of the arrow of time. So that's a movie definition of an arrow of time. So we say that an event exhibits an arrow of time if a movie of the event played in reverse represents an impossible event. Okay? By looking at the movie, you can figure out whether the movie is being played in the right direction or it is being played in reverse. Okay? If such a thing happens, then that event shows an arrow of time. I'll show an example soon. Okay, so we can tell apart when the video is played forward and when it is played in reverse. Let us take the video of a marble moving on a carpet. You can do this. Okay, take a carpet and roll a marble on it. Take a video, and so so this is a carpet. So I showed you one video. One of these two videos is played forward. The other one is played in reverse. You have to figure out which one is which. So here they are again. Is it a video being played in reverse or being played forward? Forward. Why? Because it stops. Okay? So forward, correct. This one is something in which the marble, it was a stationary marble, suddenly decides to get moving and goes. So is it forward or reverse? Speed also increases. Very good. So therefore, it's reverse. Thank you. So here you are. So this was a video being played backward. Okay? So therefore, So we see here another event which shows an arrow of time. Okay, that's the movie definition. However, you do the same experiment on a skating ring. You let the marble roll. Is it being played forward or reverse? Forward or backward? You don't know. No stopping. Okay, can't say. Very good. Here is another marble which is just placed on the skating ring. You can take a movie of this, nothing happens. Forward or backward? Can't say. Okay? Can't say. Good? So, the skating rink business shows some fundamental property of the basic laws of physics. Okay? This is called the time reversal symmetry of fundamental laws. So, in this slide, I'll use a little bit of equation business, a little bit of mathematics. This will be the only slide here, or I'll try to be as simple as possible. Okay? So, this story starts with Galileo, who realized that in spite of day-to-day observations that things in motion come to a stop, he had the foresight, he had the insight to figure out that if you take out this friction business, which is a force, if you remove all forces, then something in motion will keep moving forever. This was a great leap. You don't see such things, okay, unless of course you trying to learn skating or something like that, in which you seem to be keep moving and so on and so forth. But even then, you stop after a while. So he said that objects in motion keep moving in a straight line forever, okay, without forces. And of course, stationary objects keep stationary forever. That's no big deal. Okay, that's everyday experience. But objects in motion. So there's a little bit of equation here. That's called law of inertia. The rate of change of position is constant. This can be written as saying that the rate of change of position is equal to 0. Okay. Pardon me, only for this slide. Okay, I'm not going to use mathematics after this. So this, the last equation here, okay, this one has two rates, rate of change of position. Two rates appear here. That means that time appears twice. Okay. So because time appears twice, if you change your clock, to go backwards, that will make t going to minus t. You pick up two minus signs. Okay, that becomes a plus sign. So these two equations become the same. The equation with t and the equation with minus t, they are the same equation. This is the reason why you have this time reversal symmetry of fundamental laws. So this is without force. You might say, well, what happens in the presence of force? So that issue was solved by Newton. So motions can change with force. These laws can change. What do they become? They become this way. Okay, that two t's still appear. Okay, and then some force business appears here. Okay, I'm not going to use equations after this slide. Okay, so please bear with me. Yes. Okay, so this is called the law of motion, and again, since t appears twice, t going to minus t, okay, doesn't do anything. Okay, it's the same. These two equations are the same. All right. So the fundamental laws of motion are time symmetric. They do not distinguish between t and minus t, okay, or between future and past. Okay, if you change, of course, t going to minus t, you are exchanging future with past. These are the fundamental laws of physics. Now, let me say the same things without equations. So this is also sometimes called a mirror symmetry between past and future, okay, or t symmetry or time reversal symmetry, etc. So take the example of two marbles again. If this can happen, the reverse motion can also happen all the time without fail. If something can happen this way, you reverse the motion, no problem. Take a video of this one, this event, play it backwards, nothing fun. Okay? Both are possible. That's time reversal symmetry. So, some of you know that the world is not described by Newton's laws. It's described by, it's described by Newton's laws to a very good approximation, but if you go to the atomic world and so on and so forth, you have to change the description a little bit. That description is called quantum mechanics. Okay? So you might say, well, when you go to quantum mechanics, perhaps time reversal symmetry is violated. No, it's not violated. So take an atom, and this is my attempt at drawing light. Okay? So this is what happens. Atoms can absorb light. An example, this is an experiment that we keep doing all the time. We go out in the sun, we feel hot. Okay? So the atoms in us, they are absorbing heat. Okay? So we feel hot. So therefore atoms can certainly absorb light. And it can radiate light also. Light bulb. Okay? Atoms can radiate light, so both things can happen. So quantum mechanics therefore also shows time reversal symmetry. Now comes the question, if there is no arrow of time at the fundamental microscopic level, then how come those arrows of time which we talked about, they appear? Let me quantify by an experiment the arrow of time that I am going to talk about. This example I am going to come back to several times. So this is a gas chamber experiment. Suppose we pump in some gas. This is a chamber. This was empty, and I pump in some gas here. Okay? This is a representation of some gas molecules. After a while, what will happen, you think? It will spread out. Excellent. There you are. This is what will happen. On the other hand, if I start with this, can we end up with this one? No. Because that will happen. So if this happens to the air in this room, it just goes to a corner and we all drop dead. It doesn't happen. Okay? So if I give you a snapshot of before and after, it's absolutely unambiguous. Which one is before, which one is after. So there seems to be a conflict here. Let me give you some other lists. So this one is something that we just talked about. Air molecules, they spread out uniformly. They do not spontaneously segregate. Hot air and cold air mix to reach the same temperature. They do not spontaneously unmix. Okay? A cup of hot tea loses heat to the air and becomes cold. It does not get hotter by taking heat from the atmosphere. Okay, that would be bad. We use these arrows of time all the time. Suddenly, if we mix sugar into some tea and the sugar gets separated again, and we drink the tea, bad news. Okay, so we use these arrows of time. This is, everyday thing. A rolling marble loses energy to the molecules in the carpet and stops. So that friction business is actually some interaction between the marble and the molecules in the carpet. Okay? It could have so happened that a stationary marble, it just starts absorbing some energy from the molecules, okay, and start moving, but it doesn't happen. These all appear to be violations of the time reversal symmetry of the fundamental laws. Okay? So I hope by now I convinced you that there is perhaps something wrong. Now all these arrows of time, they can be encoded in some law. Some of you have probably studied in school. That's called the second law of thermodynamics, or it's called the entropy law. This law shows an arrow of time. Okay? So here is a little explanation. Take 10 coins. Okay? We are going to do this experiment several times. take 10 coins and toss them at once. This is a possible configuration, all heads, 10 heads. And this is another possible configuration, 5 heads and 5 tails. Okay, which one is more likely? The second one is more likely. How much more likely is this? So this is an improbable configuration. You can count this. This is 1 in 1024. Okay, 1024 possible configurations are there. Okay, head, etc. Head, tail, 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 etc. Something you count them all is 1024. Okay, this is 2 to the power 10 for people who are comfortable with such things. With 5 heads and 5 tails, okay, there are possibly 252 configurations out of 1024, so that's 25%. Okay, so this one, there is also another description. This is called ordered. Okay, it's very nicely ordered. This is disordered. Okay, this is some kind of a random collection. Okay, so the randomness increases in this direction. So this randomness is encoded how numerous a configuration is. Okay, that is encoded in some quantity called entropy. You say that this configuration has more entropy than this configuration, and if there is some time evolution, now we are talking about time evolution, then you will go from, you will go from this sort of configuration to this sort of configuration and not the other way around. So you can say, well, so therefore all the examples of the arrow of time that I have so far presented to you, they can be described, at least the everyday ones, okay, they can be described, they can be explained by the second law of thermodynamics or this entropy law. So this can explain the arrows, but then there is a problem. We are accepting the laws of Galileo and Newton and so on, and we are also accepting the second law of thermodynamics. Okay, but there seem to be some conflict between these laws. Who is correct, right? So how do we resolve this conflict? If we say that the second law of thermodynamics is correct, the entropy law is correct, then perhaps Galileo, Newton, these great guys who discovered the fundamental laws of motion, perhaps they are wrong. So is there some sort of secret time symmetry in fundamental physics that they didn't know about? Let's do some experiment. This experiment is called LHC. Some people have heard about this. This is also called the Big Bang machine. This is at CERN. So this is the picture of a huge collider. 2 protons are, being sort of accelerated to very high speed, nearly the speed of light. They bang into each other. You do all kinds of experiments and test fundamental laws of physics. There are other ways of testing fundamental laws of physics. This is a satellite. You go in space and test fundamental laws of physics. Kepler and Tycho Brahe and Newton, these guys were interested in planetary motion. So you can try to test the fundamental laws of physics, and in particular the time reversal symmetry of the fundamental laws of physics. So what do we find? Is there time reversal symmetry violation in the fundamental laws of physics so that we can explain our marble stopping? No. Almost no. There is a tiny violation here of time reversal symmetry, but that's too tiny to explain our marble stopping on a carpet, or the sugar dissolving in a teacup. So now let me try to explain to you whatever much we know about the resolution of this apparent conflict. So this experiment everybody can do at home. All you need are 10 coins. Okay, 10 similar coins will do, but if you don't have 10 similar coins, any 10 coins will do. Start with 10 heads. Okay, start with 10 heads. I don't know whether I don't even have my money bag here. So I don't want to be one of those jugglers who takes some money from the Okay, good. So you do it this way. You shake them with 10 heads. So put them here and put them here again. And take the 10 coins again and do it here again, and so on and so forth. Keep doing it. So this is an experiment which I did a couple of days back in the morning with 10 coins. Sorry, one of this belongs to you. And the other, it comes back.
This is sure not a problem.
That's right. Okay, so the result of my experiment is the following. So start with 10 heads, you get 6 heads and 4 tails. Then you got 3 heads and 7 tails, 5 heads, 5 tails. Take again 5 heads, 5 tails, 5 heads, 5 tails, 4 heads, 6 tails, etc., etc. So you go from a rather rare kind of configuration, a singular kind of configuration, to a more numerous variety, something like that again. Numerous, 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 numerous. You stay within the numerous kind of variety. Stay within a more probable kind of configuration. And I didn't have patience to do approximately 1,000 coin tosses. But if you do 1,000 coin tosses or maybe 1,500 coin tosses, then eventually you actually might come back to these 10 heads. Okay, I didn't do it, but you are welcome to try it out. Okay, presumably you will get, if not 1,500, do it up to 3,000 or maybe 10,000, you'll get it. Okay, so typically this, how did I get this number 1,000 coin tosses? This is all possible configurations. Okay, so basically the idea is the following, that if you shake the coins, okay, you start visiting various configurations. Okay, and without any further constraint given onto your system, you visit basically all the configurations allowed in the system. Okay. Once you are done with it, you can come back to your 10 heads. Okay. But that's a long, long thing. This is 2 to the power 10. So let me tell you, here's a little graph. This is not mathematics, everybody is familiar with graphs here. So basically, you start with some configuration which has a very low probability. Okay, it's just 1 in 1024. Then you go to the 6 heads and 4 tails. So there are, about 20% of such configurations. Then you come down a little bit and so on and so forth. But mostly you stay in the high probability region. This is some experiment which you can do, and I'm not kidding. Okay, you can actually do this. This will eventually happen. Okay, computer experiments have been done. Okay, in which one sees this. Okay, so although I have not done it, I didn't have the patience. Computer experiments have been done in which you see that the things do come down later on. Okay, so here is another representation of the same event. So these are the actual configurations. Okay, all heads, then some 6 heads and 4 tails or something, or maybe 5 heads and 5 tails. You keep going like this. So there are lots and lots of configurations in this blob, okay, which are sort of equal numbers of heads and tails. Okay, and there are some guys, like all heads or all tails languishing outside of this big blob. Okay, and eventually when you are done with all this, okay, you can come back there. Okay, but it takes a long, long time. So now, what is the point? Okay, why did I suddenly go into coins from molecules? Okay, so this is the point. A lot of the molecular collisions, but not all, is like shaking of coins. So what happens is that when you have gas molecules, at some corner, etc., they are all moving. These guys are all moving at some speed, and they collide with each other. Okay, various molecules are coming and going, and they are colliding with each other, and so on and so forth. That's like shaking of coins. Okay, that's like shaking of coins. So every few seconds, every few microseconds or something, you are shaking these coins and shaking these molecules. Okay, so all heads is like this kind of a molecular configuration. Okay, that's very, very ordered, very, very rare, or very, very improbable. Okay? And things like this are right in the middle. There are many, many such configurations. So you keep traveling here like this and so on and so forth, and eventually you will end up there. In fact, there is a theorem proved by a famous mathematician called Poincaré. He proved that you will eventually come back there. Okay? So that's called Poincaré recurrence. So eventually, after many such shakings, the molecules can, and they do, go back to the original configuration. However, if there are n molecules, okay, so in my experiment with the coin tosses, how many coins did I take? 10. Okay. And when did I say I would come back? After about 1,000 shaking of coins. Okay. That was approximately 2 to the power 10. Okay. Similarly here, if there are n molecules, the time taken for this Poincaré recurrence, for everybody to come back, Poincaré recurrence is like all molecules go to that corner of the room. Okay. That time would be proportional to 10 to the power n, where n is the number of molecules. Okay. 10 to the power n, 2 to the power n, these are all the same order of quantity. So approximately 10 to the power n. That is 1 followed by n zeros. Okay. So in this room, okay, I have let the cat out of the bag already. So in this room, how many molecules are there? Okay, so it's roughly that. So n is roughly 10 to the power 24. So n itself has 1 followed by 24 zeros. Okay. So the time taken for all the air to go back to the corner would be 10 to the power n. So that will be 10 to the power 10 to the power 24 times the time for a single shake. Okay. So this turns out to be some number which has 1 followed by, okay, so for those guys who are, so here it is, 10 to the power 24 is also called 1 million billion billion molecules. So you have now 1 followed by 1 million billion billion zeros. So I thought that, I would start writing something like that, but it's a bit too much on your patience. So here it is. So you can't wait. So 1 followed by this much, and it turns out to be, in fact, such a large number times the age of the universe. So that, of course, is an impossibly large number. So you may very well say that the reversal does not happen. Okay? It takes such a long time that the reversal does not happen. So here it is. These are impossibly large time scales. Hence, for all practical purposes, we see the occurrence of only improbable going towards probable, and the other thing we don't see. Okay? So this is why we see the settling down of systems. Some highly energetic object like the marble or the teacup, it shares its energy with the surrounding. Yes, please.
Was that the maximum amount of time that would be taken for the recurrence, or could it happen sooner?
So in a particular experiment, it could happen a little sooner. Okay. In a particular experiment, it could happen a little later also, but on an average, okay, it would take that sort of
so it's not
time.
impossible for it to happen right now.
It is possible. It is possible, certainly, and but it is possible. It is possible. It is possible that in this thing, it sort of make a small sort of excursion into this and goes back. Okay, but it's very, very, very improbable. Okay, so in many runs of this kind of an event, okay, it will happen. Very, very. The numbers that we are talking about is really that large. Okay? It's the 10 to the power 10 to the power 24 and so on. That's a very unlikely event, but in principle, yes, of course, that is indeed true. So here we are. So therefore, we have understood why things go to equilibrium. Why things? Yes, please.
After this first time, a marble can also start rolling on its own.
Absolutely, absolutely. You have got it. okay, and the sugar which is mixed into the tea can start separating out, and so on and so forth. Okay, it can happen. Okay, so but we have sort of proved that it takes an impossibly large time, so therefore we exclude that. This shows that the entropy law is not a perfect law. The entropy increases, and then after a very, very, very long time it can come down. It's not a perfect law. Fundamental laws are the perfect laws. Entropy law is a law which can be violated, just like what you said, that if it so happens that in a particular experiment, the gas molecules decide to come back soon, etc., etc. There is some other fun thing that we can say here. So here it is. So we have explained this, have we? Sort of, it seems, but not quite. Okay, why not? So let's go. All systems do not behave. Okay, their interactions do not behave like the shaking of coins. Okay, the solar system is one possibility. So I have already explained at the beginning of the talk that if you take a picture of a new moon and the full moon, you can't quite figure out which one is before and which one is after. Okay, these are periodic systems, and we hope that there will always be a new moon after a full moon and a full moon after a new moon. If there is some arrow of time there, okay, then that's bad news. Okay, so this better be a stable periodic motion. So the solar system has, of course, many, many more configurations in which the planets and the asteroids and comets and so on and so forth, they are all messed up, mixed up, and it's a complete mess. It could go to that sort of a configuration. So such configurations, of course, exist, okay, but it never goes there. Okay, there are enough interactions. Okay, normally when we study in school, we say that, well, the Earth, okay, moves under the gravitational force of the sun. That's not the only thing. We have a big planet, Jupiter, okay, which just missed being another star. So the Jupiter also pulls the Earth. Even the tiny asteroid guys, they're pulling the Earth. We have neighboring planets. There are some planets which are quite big, and so on and so forth. They come close. Often you have these doomsday predictions that my God, we are going to go out of our orbit by slingshot effects and so on and so forth. Okay, but we seem to remain stable, periodic. The year happens, day happens. The moon, the sun, and the Earth. These systems, along with everybody else, seem to execute a stable periodic motion. Okay, so they are. It's not as if we are not being shaken. We are being shaken. Okay, but this shaking is not like the shaking of the coins. Okay, that's why the planetary system is not showing an arrow of time. Okay, by looking at a snapshot 1 and a snapshot 2, I can't figure out which one is before and which one is after. Okay. So if the shaking was like the shaking of the coins, we could turn up, the solar system could turn up in a mess like this. Okay, some complete mess of asteroid dust does not happen. So some systems show order and periodic motion, while some others show dissipation and settling down. They settle down to equilibrium. Okay, so we have explained that in some system, all right, okay, systems which behave like the shaking of the coins, we have dissipation and we have equilibration, but there are other systems, okay, both are useful to us. Dissolution of sugar in tea is useful to us. The solar system being stable and periodic is also useful to us. Okay, how do we know beforehand which one is which? Okay, how do we know that the solar system is going to remain stable like this? Okay, so this is some problem which has been studied for more than a century by now, starting from the great mathematicians of the 19th century and so on and so forth, led by Poincaré and so on. And so let me say a little detail about that. So how do you know which one is which? So here it is. There's a specific arrow of time, and here we don't know which one is which. Okay, so that's a pictorial representation of what I have been saying. So there are this gentleman. He is called Kolmogorov. Arnold and Moser, all famous mathematical physicists. They have studied for decades conditions under which, okay, a periodic motion would remain periodic under perturbations. Okay. They have come up with a great theorem called the KAM theorem, okay, which says that perhaps the solar system is stable. Okay. Perhaps we are not going to get into a mess of asteroid dust. And there is this other gentleman, he is called Boltzmann, okay, who is credited with the entropy law, okay, and this is Sinai, who has studied a property of systems called ergodic property, that is the shaking property or the mixing property of systems. And this is another gentleman called Lyapunov, who has studied systems like chaos, which is a tendency which is opposite of periodicity, regularity. Okay? That is irregular motion. So, there is like a tug of war between periodicity like that and dissipation like that. Okay? So, which one is which? Okay, that is the question. This is an unsolved question. Okay? Given a particular system, okay, do I know that it shows dissipation, or do I know it's so you have to study a little more. So, in a large class of cases, okay, much like the case in a teacup, the answer is that it shows settling down, it shows dissipation, or it shows the tea getting cold and so on and so forth. The answer comes from a completely different area of physics, which you hadn't predicted that the answer will come from there. Okay? That's black holes. And there is an arrow of time for black holes which I didn't tell you about. I mean, I didn't tell you about this particular arrow of time, but let me tell you now. So, black holes are objects which are so massive, okay, that something when it goes in, okay, it remains trapped forever there. It just goes within a neighborhood of the black hole called the inside of the event horizon. If it goes near enough, it's sucked in and it never comes out. It just never comes out, period. So, this is a picture, I mean, this is a sort of cartoon representation of a famous black hole in the sky. It's called Cygnus X1. Okay. You don't really see anything there. This is a cartoonist's impression. You see a visible star. So, this is a binary star in which there is a visible star, and there is something here. That's something which is, sucking in a lot of the matter of the visible star. By looking at this, and also by looking at some X-ray emission coming from here, okay, you figure out that there is something there. Okay, that's a black hole. Now, it's universally agreed by astronomers that there is a black hole there. This is called the Cygnus X1 black hole. And so, now let us do an experiment. This is possible. Okay, this is allowed. This is impossible. Okay, I just argued for you that the black hole is so massive that nothing comes out. So, therefore, there is an arrow of time. This is very different from this situation. Okay. So, the fact that black holes exist, okay, were theoretically argued by Einstein's theory, that's Einstein. The possible generation of a real black hole, okay, was argued by Chandrasekhar. And this gentleman, as many of you know, is Stephen Hawking, who said, well, look, so there is there seems to be a time asymmetry in black hole physics, but there is no such time asymmetry in quantum mechanics. So, therefore, black holes violate quantum mechanics. His argument was a little more sophisticated. Actually, things do come out of that black hole, but what comes out is not what went in. Okay, that's called Hawking radiation. So, with all that, they said that, okay, he said that the black holes violate quantum mechanics. Now, there is a resolution of this, which I cannot go into it in great details, but roughly speaking, the resolution is that the black holes are made of very tiny vibrating strings. Okay. So, there is a model of black hole. You can actually construct, okay, a black hole solution from string theory, okay, in which this black hole is, here's a black hole, and the black hole is represented by these tiny vibrating strings. Okay. These shake like molecules. Okay. So, the black hole is represented by a thermodynamic system, a normal kind of thermodynamic system in which strings just behave, they collide with each other, they behave like molecules. Okay. So the strings are bouncing about much like air molecules in this room or like molecules of tea in the teacup. Hence, the black hole arrow of time is just the arrow of time, second law of thermodynamics. Okay. So, there are popular articles on this. Okay. I wrote something in the Scientific American India 2010, but there are many others. You can Google search, do these things, you can ask me about the possible literature. So, roughly speaking, this is the equation that you get. Okay. That the teacup is essentially related to a black hole, and the arrow of time of the black hole can explain the arrow of the time of the teacup, okay, or vice versa. And in much like this arrow of time was only approximate, this arrow of time also is only approximate. Why and how the black hole arrow of time is only approximate? Yeah, hi.
You had mentioned before that when something comes out of a black hole, it does not come out the way it went inside.
Right.
So, does that say that when you put the sugar inside the tea, when you fish it out of the tea,
Right.
it does not come as the sugar was put inside?
So, well, that's a very good question. So, there is no direct analog of Hawking radiation in case of a teacup. What comes out of the black hole, okay, is indeed some other thing. If you wish, that's a very good question. So, if you wish, you can ask the following question, that suppose I put a lot of stuff in a hot cup of tea, and I stay outside of the teacup, and by the heat that's coming out of the tea, just by watching the heat, can I figure out what has gone into the teacup? Okay. So, that question is like the question of Hawking radiation. The stuff that comes out of the, so some people want to say that the stuff that comes out of the black hole, okay, is enough to say what has gone in. It's a different thing that is coming out, okay, but it's enough to say what has gone in. That information is enough. Okay, so the information can come out, although that particle cannot come out, and that's enough to say that there is time symmetry. So you put some sugar in, okay, some heat comes out, okay, and some just by watching the radiation that comes out. Roughly speaking, it's like that. But a better analogy even is that you take a furnace. Okay, have you ever seen a furnace? Has anybody ever seen a furnace? Yes. All you see is a red glow. It doesn't matter what is burning inside. Okay, it's just red glow. You put a lot of stuff inside, only a red glow is seen. Okay, that seems to be time asymmetry also. Because if you want to sort of go back in time, okay, various different kinds of things could be put in. Okay, just some red glow comes out. So the assertion is that by watching the minute details of the red glow, okay, you can figure out, you know, by looking at the spectrum, looking at the wavelengths of whatever comes out, you can figure out what is burning inside. Okay, thank you for the question. It's a lovely question. Okay, so here it is. These black holes, some exotic objects which are described by Einstein equation, and here is hot tea. That is described by equations due to two gentlemen called Navier and Stokes. That's called Navier-Stokes equation. So there's some beautiful connection between Einstein's equations and Navier-Stokes equation that have been found out in recent years, and therefore the black hole arrow of time. When I say equality, you know, There's some math that goes into that. There's some parameter that you have to vary, okay, to see both the arrows of time. But these are all very exciting developments and which are still ongoing. Okay, not everything is known about this equality and so on. Let's come back to the arrow of evolution. Okay, I'm near the end of my talk. This is something which is very, very difficult to understand. Okay, we had some, monocellular species. Excuse me, sorry, this sapiens has come in the wrong place. Sapiens should be here. This should be over here. So you have some monocellular organ. This shows if you prepare a slide when it is late night, such things can happen. Okay, so this should be here. So you have some what? So this is a monocellular organism. An example that I gave here is called E. coli. Okay, it's some simple enough thing. There are people in the audience like Sudipto here who would probably know much more about such things than me. But over the course of evolution, which took millions of years and so on and so forth, other more complex organisms, vertebrates, human beings, and human beings as intelligent as Ramanujan, such evolution has taken place. This is very surprising. And here it is surprising because it seems like order is coming out of disorder. Okay, more and more ordered stuff, more and more organized stuff, like human beings. These are so. In fact, this arrow is even more surprising in the next one. That's the origin of life. Okay, from inanimate object. Okay, so it is believed that there was some in the beginning. The Earth was a very hot place, some hot primordial soup and so on and so forth. And, so people have tried to do experiments in which animate life comes out of inanimate objects. No such luck. Maximum that has been found is in an experiment by Miller and Urey and so on, okay, in which amino acid, which is one of the basic ingredients of life, that has been formed, but no life. Okay, so life from the primordial soup is yet another cup of tea. So the primordial soup was a mess like this. Okay, so this is like a whole bunch of heads and tails and so on and so forth. This is disorder. Comes extremely ordered objects, DNA, life, and so on. That's like all heads, order, life has appeared. This is unknown. Arrow of life is unsolved. Excuse me. Is unsolved. Cosmological arrow of time. We live in an expanding universe. There was a beginning of the universe and so on and so forth. Why does that happen? What happened at the origin? What happened near the origin of the universe? Okay, so that is also unsolved. So there are all these beautiful unsolved problems for young members and older members in the audience to solve.
Can I ask you a question?
Yes.
What is the probability of the Big Bang being right, and what is the possibility of Big Bang either is right or not right?
That's a good question. So certainly, from this point onwards, from a few very small fraction of a second onwards, the picture of the universe is like this. That has been now observed and explained with established and but so for example, if you want to go back to times which are, if you call Big Bang as t equal to 0, and if you want to go back to times like 10 to the power minus 40 seconds or something like that, that's 0.000, 40 zeros and 1, then you can't say. But otherwise, the picture of the Big Bang, from those small tiny scales up to now, okay, are now sort of unanimously agreed on, and it has been established. Okay, So, or at least from time scales which are a little bigger than that, but so various. I mean, there are various alternative models of cosmology. They have mostly been ruled out or are being ruled out, and so on. There are details. There are details here. There are values of parameters which have to be fixed, but the general picture of the Big Bang, along with some other hypothesis called evolution, inflation, and so on, that's known. So this is also sort of an unsolved problem, and thank you.
What I think we should do is, it's closing in to 12, so let's have a chai. Beyond that, the chai also will go cold, and we can have a small session of, say, very informal questions there, but we'll come back here in, say, 10 minutes and have a round of questions as long as we can permit. The theatre people will try and throw us out by 1